All right, so so today we're going to take it further. We'll take it to the so we're going to continue with virtualization. So as we spoke about the characteristic of virtualization, we know that isolation, which means the machines are not connected in terms of damages. So once there is a damage one side, it doesn't mean damage. Okay, so there is a few issues that we spoke about yesterday, which are related to virtualization, and we also spoke about the level of privilege of the x86 architecture. So where the x86 CPU architecture will be defined by 4 privilege level, which we call rings. And these privilege levels calls rings will help us control the hardware and the memory. So you have from ring 0 to ring 3, right? With ring 0 having the highest privilege and ring 3 having the lowest privilege. Okay, so today we're going to start by talking about mapping between CPUs and virtual CPUs. All right. So when we talk about mapping between, mapping between CPUs and vCPUs. vCPUs just mean that it's a virtual CPU. So this is so when a hypervisor, I don't know if you remember yesterday we spoke about an hypervisor. So the hypervisor like a FusionCompute, KVM, VMware, those are just softwares that will help you actually create this virtual machine. So those software helping you creating the virtual machine are called hypervisors. So when a hypervisor runs the virtual machine, it has to map virtual CPUs, right? It has to map all the virtual CPUs which belong to a certain virtual machine onto physical CPUs or PCPUs that belong to the physical host. All right, so that's how it's mapped them. So the hypervisor is the one that is in charge of doing that. All right, so so how's virtual CPUs map to physical CPUs? So each virtual CPUs assigned to a certain virtual machine is just scheduled. It's scheduled on one of these 32 logical processors. So we have an example of 32 logical processors, which when we talk about the logical processor, it's something that is virtual. So each virtual CPU is assigned to one of the 32 processors. So the hypervisor CPU scheduler will decide which physical core will run each vCPU, right? So this map here is created by the hypervisor. So multiple virtual CPUs can share the same physical core, right? That's possible, but not at the same time, right? So they basically like take turns like a queue. All right. So so the numbers of CPU running on a certain node can exceed the actual number of virtual CPUs, right? When we this means that we can actually allocate more virtual CPUs to the virtual machine that there is CPUs trade. So you have this trade here. So when you look at the trade, we can actually allocate to this trade. We can actually allocate many virtual CPUs. So that is possible. Okay. So so for example, your host have 32 physical CPUs available. So you can create virtual machine totally like having 64 or even 128 virtual CPUs depending on the workload. All right. So what the hypervisor will actually time how these CPU will be accessed by the virtual machine. So as I said, they are accessed like a queue. So they actually take turn to be accessed. So we have a memory virtualization issue that can. So when we talk about memory virtualization issue, so when we dealing with virtualization, right? So it's very important to understand the memory virtualization. So in a system which is not virtualized, where we have all the physical servers, physical operating servers, and all the machines, so that is like a traditional non-virtualized environment. Okay, so in that type of environment, the operating system will assume it's like it owns all the physical memory. So the operating system take control of everything. It will manage all the memory starting from the physical address. It expects the memory to be continuous, which means that the operating system and other applications think that the memory is one big unbroken block, right? Think of your laptop and everything. So the operating system consider if your laptop is a 256 gigabytes, your operating system will consider the whole memory there, which is different from virtual machine, because in virtualization, we have multiple machines that can be assigned certain memories. You can't just find the operating system looking at the whole memory of the server thinking that it can use the whole memory. So with memory virtualization, we're going to have a memory virtualization issue, which means that there is only one physical address, 0, right? Which means that it cannot meet concurrent customer requirement. So if there is many virtual machine requesting the same thing, it can't meet that. So the physical address 0 is only one. So when multiple virtual machines are running on the same host, so each guest, which are those multiple virtual machines, so each guest operating system expects to start its memory from 0. So when you think about it, remember when we talk about virtual machine, we say you can have 4 virtual machines. That means the first one maybe is using Windows 10. The second one is using, I don't know, Red Hat. The third one is using Ubuntu. So they are all using different operating systems. And each operating system of this virtual machine expect to start its memory from address 0. Right, but there is only one address 0. That becomes a problem. But there's only one real address 0 in the system. So this is one of the issue, is that the memory starts from physical address 0 cells. So all these guest operating system will start the memory from address 0, while there's only one address 0, which cannot meet multiple concurrent customer requirement. Okay, so if all the guest operating system tried to use physical address 0, they will overlap and corrupt each other's memory, which will crash the system. All right. So the second problem that we're having is the memory allocation efficiency, right? So so when we look at the second problem, the contiguous memory allocation and efficiency, so although we have consecutive physical addresses that can be allocated, the method of memory allocation leads to a poor efficiency. Why? Because when you look in traditional system that we have, the operating system will try to allocate blocks of memory. Example, you have 1 gig from address 1000 to address 2000. So there will be 1 gig allocated to that. However, when we have, however, the physical memory can actually become fragmented over time, and we have now an issue with finding these blocks, or or controlling or allocating the memory properly. All right. So the memory blocks, we can say the memory blocks have contiguous addresses. All right. So the solution, okay. So the solution to this will be to use the memory virtualization. So memory virtualization will solve these issues by using address mapping layers. So instead of directly using physical addresses, each virtual machine is given its own virtual address space, so that there is no overlapping of virtual address space. So basically, we can have, let's say, we have virtual addresses per virtual machine. So each virtual machine believe that it starts from 0, yes. So, but in reality, what we're gonna do, the hypervisor, which is the software that creates virtual machine. So the hypervisor or the VMM, which is the virtual machine monitor, right, will map these virtual addresses to different physical location on the host. So example, you have your virtual machine, you have maybe 3 virtual machines. So the 3 virtual machines, we're gonna have the guest address. The guest address, we can keep all of them. Maybe, I don't know if this can allow me to write here. Wait a second. So we basically have, so we have maybe a virtual machine 1, which will have a guest address of maybe, because they all need to start from 0. So we have 0x, and then we have 0, 0, 0, 0. Okay. So we have even like 7 zeros there. And then virtual machine 2, because it's expecting to start from 0, we're going to have the same guest address. But the actual physical address for this one, maybe for virtual machine 1, the first digit here, it's going to be 1. So we're going to have 0. We're going to have this pattern 0 times 1, 0, 0, 0, 0, 0. And then 0 times 1, 0, 0, 0, 1. You understand? So depending on that. But and then the virtual machine 2 will have 0 times 2. 0x2 and then 0, 0. The virtual machine 3 will have 0 times 3. And then you understand? So we actually separate the physical address. So each guest operating system thinks that it's memory starting from 0, but the virtual machine monitor translates this address to unique physical region. So that can help. Okay, so there's many methods that can be implemented there. Okay, so virtual memory virtualization. We actually having the physical memory of the machine that will be managed centrally can be packed into multiple virtual memory of multiple virtual machines. So, which means that when multiple virtual machines run on a single physical host, they all believe they have their own dedicated memory, which means a memory starting from address 0. However, in reality, all virtual machines share the same physical memory, which is the RAM of the host. Remember, we have the host will have its own RAM, so the host can be a certain server that all these virtual machines are using. So, in reality, all the virtual machines share the physical address of this host, which is the RAM. So, we achieve this illusion safely, and that's how memory virtualization is used. So it's kind of creating this illusion by creating all these addresses pattern, so that all these operating system thinking that they are starting from address 0, while they are actually these addresses have been modified. So what you look at, you have the guest virtual address, guest physical address, and the host physical address. So then we're going to have the KVM, which will virtualize and use physical memory and allocate its VMs as required. So this is how the KVM will handle memory virtualization. That means that the physical memory, which is the RAM of the physical machine. So when we talk about PM here, the physical memory of the PM, this is the physical machine. So remember, the physical machine can be the server that is being used by all these virtual machines there. So the physical memory, which is the RAM of this physical machine, will be managed centrally by the KVM hypervisor, right? So the KVM will allocate the kind of portion of physical memory to each virtual machine. So think about it like when you're using on your computer, you need to use maybe 5 apps. So instead of having 5 apps on, and you know that that's going to affect the whole memory, let's say your RAM, you have an 8 gig RAM. So if your software, you have one software that is already using 4 gig RAM, so what will happen is that the rest of the software has to share the other 4 gig. And if they cannot share that, and then your system is really slow and bad. So what we do here, the hypervisor, in that case, the hypervisor will actually allocate a memory for each virtual machine. So the KVM hypervisor will allocate portion of physical memory, which is the RAM, to each virtual machine as needed. So each virtual machine will see this allocation at its own, as if it was its own physical memory. So if the whole physical memory is 8 gig, for example, so you have 3 physical machines. Let's say you have 4 virtual machine, you want to allocate 2 gig per virtual machine. That means that each virtual machine will see this allocation as its own physical memory. But in reality, it's just a virtual view of the host memory. Right. So in KVM, each virtual machine will run as a process on the host. Okay. And then the memory used by the virtual machine is actually the memory allocated to that process by the host operating system. All right. So and then we have input-output virtualization issues. Okay. So input-output virtualization will just allow multiple VMs, the virtual machine, to just share the physical input-output devices. So the input-output devices, you have like your network cards, your USBs, the disk, right? So this I/O virtualization will just allow multiple virtual machines to share the physical input-output devices of a single physical machine. So these virtual machines are going to share maybe the USB ports, the any other input-output device. Okay, so it's going to share with the physical machine, while at the same time it's making the virtual machine think that it has its own dedicated devices. All right, so this is just the main goal of this is just to allow a safe sharing of hardware and devices, and also by making sure that there's also an isolation between the virtual machine. Okay, so this can really provide an efficient performance, right, in terms of the system, right? So you have your there is certain core function of the FusionCompute input-output virtualization. So you have, for example, the device discovery, the 2 functions of the FusionCompute. Like you have the device discovery and the access interception. The device discovery, which means that the FusionCompute which is, remember, the FusionCompute is the hypervisor, which is the software that creates the virtual machine. So the FusionCompute decide and control which physical devices can be accessed by which virtual machine. So this will present the virtual devices. Example, you have your virtual disk controller for each virtual machine. So the guest operating system inside the virtual machine will detect these virtual devices as if they were like real hardware devices. Understand? So and then you have your, remember we spoke about the NIC card, right? So an example can be the physical host has one NIC card, right? So if the physical host has only one NIC card, so the FusionCompute, which is the hypervisor, the software that creates this virtual machine, will create multiple virtual NICs for several virtual cards. But the reality is that we only have one NIC card. Does anyone still remember what is a NIC card? Anyone still remember?
Network interface card.
Perfect. So the network interface card, that's the card that you have on your device that's deal with the network. So basically that hardware component that you have on the motherboard of a computer that will actually connect the computer to a network, you know. So it's basically in charge of all the transmission of the data through the network. So now when you look at it now, that way on the card that you have, the NIC card, that way you have the ability of connecting your Ethernet cable, Wi-Fi. So when you have this host, let's say you have a machine, this machine only have one NIC card, but you've already created 4 virtual machines from that machine. So 4 machines, which are virtual machines, are using this machine. So now this software, the FusionCompute, will create multiple virtual NICs cards. So these virtual machines are thinking that they have their own NIC card, but it's actually they are sharing the same one. Okay, so each virtual machine believe that it has its own NIC card, but in reality, they all share the same physical NIC through the virtualization layer. All right, so I hope that is clear. So, and then the second function of the Fusion virtualization is to also implement an access interception. So access interception, you need to understand when a virtual machine access a device, for example, like reading data from a disk or sending data through the internet. The access request will go through the input-output port, which means if you are sending it through by clicking on the mouse, that is an input-output. That's the output input device, you know. So you have the VM that will access the device. So if you're using a mouse or anything like that, and the memory, and then the FusionCompute will intercept this operation to just try and control how the virtual machine communicates with the hardware. And then the virtual machine monitor will decide how to handle the request, either by emulation or direct assignment. You know, so when you're trying to access a certain device through the internet. So there's kind of a process there. All right, so to just simplify everything, you just need to understand how does input-output virtualization work. The guest operating system inside the virtual machine try to send data through a virtual device. You have your input-output request that goes to the virtual drivers in the virtual machine. You also have your FusionCompute that can intercept that request. See, so and then we have so when still talking about I/O virtualization, which is basically very, very important, very crucial. What time is it? Okay. Very crucial here. So when we look at the I/O virtualization, this can be viewed as an hardware middleware layer, right, which is positioned between the server components, the operating system, and the I/O processing unit, which are your network card, your storage controller, your USB interfaces. So this I/O virtualization will actually allow all the multiple guest operating systems which are running on the virtual machine to share, to reuse all the hardware, such as your USBs, your external hardwares, and all those things. Okay, so that's what we're going to do with that. Okay, so we're going to have a full emulation, right? Which is the software that is used to emulate a specific device. So a full emulation here. So we're going to have a software that will be used to emulate specific devices, which means that when we have a device emulation, so the software will completely simulate the hardware behavior to a specific device, which is the virtual machine in that case. Okay, so this is how this virtual machine is going to learn to interact with this device. So how does it work? It means this software will just emulate hardware registers, interfaces. So the same input-output interface are used in real devices. So in real devices, we have things like those programmable card, the direct memory access, you understand? So you have all those card and devices, but in this case, we have them on a virtual level. All right, so you'll have multiple context switches that are required for all the input output operations. So which means that each input output operation will require multiple context switches. And those context switches are, you have your VM, which is also an hypervisor. You have Kimo. Okay, so this is how. So a few advantages that we're going to have when you virtualize these input-output devices is that we have a low hardware dependency. So we don't have to be having so many hardware because we can actually use one hardware, but we're using it on multiple machines, which are the virtual machines. All right. Okay. So that's how we can have an easy emulation. That means we can emulate many popular devices. You know, the compatibility. You don't have to change anything on the guest or the host operating system. All right. All right, guys. So this is how we can do that. So you must understand when we talk about emulation, it's just creating a virtual version of something. For example, when you have those softwares like that can help you to create like an Android emulation, it means you create a virtual phone, Android on your phone, on your computer. It looks like a phone and it works like a phone. So you can test if you create an app instead of you actually install it on a real phone, you can use an Android emulator. So this is the same way when you think about it. So in this case, but what are we emulating? We are emulating these input and output devices. All right. Okay. So so we also have the virtualizing of special devices. Okay, so virtualizing of what you call that, of special devices, so, or special drivers. Guys, anyway, so far is everything fine? Can you guys hear me properly? You can see my screen, all is well, because the class is really quiet.
Yes, sir, we can hear you.
All right, perfect. All right, so we now here have how we can have the back end driver, the front end drivers, and different drivers and devices, which we can actually virtualize using the hypervisors. All right, so when we look at that now, we have special devices drivers, right? Including the front end drivers on virtual machine, the back end drivers on the host, and then we have an efficient communication between the front end and the back end drivers, which is can help reduce all the transmission overhead between virtual machines and host. So we have a memory that is shared between the front end and the back end. So the hosts and the guests are sharing the same. So when we talk about virtual, it's virtual will be the kind of a virtualization framework which use the KVM, the key moves to improve input-output performance by just reducing the overhead of full emulation. So this is another way of doing things. So instead of fully emulating a hardware device, Virtual will just provide a kind of a standardized interface. You understand that both the hypervisor and the guest understand, the guest operating system understand. So how does it work? You have the guest operating system which use virtual drivers, right? That will communicate directly to the host virtual back end. All right. So we're gonna go from this. So the application will help you. So basically, this application will help you to communicate directly to the host virtual backend. All right. So and then you have the hypervisors. So the hypervisors that can, in this case, we will use KIMU or KVM, which will provide a virtual device to the virtual machine, such as, we have different devices. You have, for example, you have what we call VirtualNet. VirtualNet is for the network. You have Virtual BLK, it's for block storage. You have many other virtual devices that you can create. Okay, so as we said here, we mentioned the key component. We have the front end, right? The front end, which is the virtual front end. This is the driver inside our virtual machines, actually. And then we have in the back end or the host, we have the virtual back end, which is part of the hypervisor, right? So this will help us handle all the input output with physical devices. All right. Yeah, I think, guys, this will be all for this session. The next session, which has to do with HCIA-AI, HCIP-AI, will be by 6:45. And by the way, guys, I think I've mentioned that before, that it is very important to attend classes and